mentioned by my previous speaker. Um, um, good evening, everybody. I am here to speak on the topic of the evolution of old quantum mechanics into new quantum mechanics. This is a very exciting topic to learn because everybody who enters physics, it's like, oh my god, quantum mechanics have to start. This is so interesting. Quantum entanglement, one particle is here and there. It's very, very interesting for new people, but they don't understand what research has gone into it and how many people have dedicated their whole lives to understanding this theory. Niels Bohr, one of the leading scientists of the 20th century, he once popularly said, I think you all know, that a person who says he understands quantum mechanics, either he is mad person or either he is blind. So it is true. Quantum mechanics is one of the most toughest subjects on earth right now, and still now we don't know the complete picture of what it is and how it functions. And it is a very complex theory. But today I am not going to talk about just quantum mechanics. I am going to talk about how the old quantum mechanics, like how when Planck entered it, when they were the quantum mechanics was basically classical mechanics with a touch of probability. After how did that turn into the new quantum mechanics? How the probability entered, how Schrodinger entered, and why did they enter? What was the need? We're going to discuss that.
तेरा लाख ही खड़ा है भाई, तेरा लाख खड़ा है.
You have to listen and imagine. Okay. Like. Just imagine with me. I think you will be able to understand this. Just think of a ray of light. Just think of a ray of light, and it is traveling from the sun to the earth. Everybody, please. I want to be engaged. This will be interesting if you participate.
Okay,
Just think
fast.
about a ray of light that is exiting the sun and entering into the atmosphere of the earth. A ray of light. We all know that the speed of light is the maximum speed we can achieve. We have learned that 15 to 10 to the power 8 meters per second. But why can't something go beyond that? Why can't we go beyond that? Our imagination can. We can imagine if we are going beyond the speed of light. So let us just think what will happen if we travel alongside light when it is coming from the sun to the earth. A very surprising fact from the Einstein theory of special relativity. If we are traveling at a speed of 99.99999999991% speed of light, then the Earth will be seen just 17 meters wide. The diameter of the Earth will be just 17 meters, nothing more than that. So I think like these things, they're really, we cannot believe what is happening. 17 meters of Earth, the diameter of Earth is 40,000 kilometers. How can it just be 17 meters? Or if anybody has seen the movie Interstellar, when the person goes into the planet and he returns, almost 7 years has elapsed. How can that happen? How can these crazy things happen? It is all this is all theoretically true, and it is helping us to synchronize geosynchronous clocks, the aeroplanes, and the space shuttles all around the globe. Without this theory, we cannot do that because uh, I just want to start now. Why was the need of quantum mechanics? I will start with that. Yeah. Anyway, in the beginning of the 20th century, there was a very big problem in physics. That was the ultraviolet catastrophe. You have to imagine that, and this is the story. Just you will get finished in 10-20 minutes. The question was, we all know Stephen's law that it is like when if there is a black body is a black body is an object that can emit and absorb all radiations. So when a black body is active, it emits radiation. The radiation emitted by the black body depends only on the temperature, as seen here. So if you keep increasing the temperature at a point, this will glow like anything. This will glow like the sun, or more better than infinitely bright. But that is not possible. When we see the graph, we see that when we increase the temperature, the graph, the radiation increases, but after a time it falls, and it will never reach the ultraviolet zone. But when we calculate using this formula, it is seen that if we go to the ultraviolet zone, UV rays, then the light will be infinitely bright. We cannot adhere that. We cannot understand what is happening there. And it does not happen here. That is just a problem. And nobody in physics at that time could solve this. And it was a very big problem for the physics at that time. So then comes Planck. Max Planck on 14th December, which is 2 days from now, in the year 1900. He publishes the most famous, the most, what is the word? The most
Ridiculous.
mind-boggling theory of all time. For him, it was just a trick. Max Planck believed it was just a trick. He thought of light as not as a continuous spectrum, but as a discrete particle. Like he thought, like, why take light? It is going like this. We take light as small packets, and he called these packets quanta. And from there, the name quantum theory, quantum, the origin is there. And when he used this technique, the problem was solved. When he calculated, the problem was solved, and everybody was like, "Wow, this is interesting. How did this happen?" But for Max Planck, he thought this was just a flaw. He did not think it to be a real theory. The real change happened when in 1905, Albert Einstein used this theory to prove to explain the photoelectric effect. And let me explain photoelectric effect. Many people don't understand what photoelectric effect is. Just think of it as this: you are sitting in your room using your phone, and your mother calls your name. Yash, you are like, I mean, after a certain voice, like, Yash, then you like, have to go. That is photoelectric effect. When there is very less intensity, the electron will not go up. It will like I will say, I don't know. But when the intensity will increase above a threshold, then it will run. I have to. And the more the voice, the more kinetic energy it will take. That is photoelectric effect. It is very. I can put the board, fill the board with equations. Nobody will understand anything. Main thing is understanding the concept behind it. So Einstein used the quantum, these packets of energy, to explain the photoelectric effect, and it worked. And in 1905, Einstein blowed the world of physics. He put out paper on photoelectric effect on Brownian motion, and finally he did one thing that changed the physics of forever, and that was deriving E equals mc square, the most famous equation in the world of physics. He derived this, and he literally said that light has mass. Because if you go there, it was his statement that light has mass. But because of this equation, something came out that Einstein did not himself like. Einstein famously said that God does not play dice with the universe. Why did he say that? We'll come to know about it. This is about the old quantum physics. Like we are going about like Planck did this theory, and it is basically classical physics, but with a touch of probability. And Einstein published this. This was the reason for the development of the atomic bomb later in the 20th century. And then happened Niels Bohr. In 1913, Niels Bohr published his theory of atomic theory. Now, Rutherford had already explained what an atom should look like: electrons, like planets, and the sun is in between, the nucleus is in between. He explained it like that. But there are many problems. Maxwell theory stated, you have to study the Maxwell theory stated that if a charged particle is accelerating, it must radiate energy. And when it radiates energy, it will ultimately collapse into the nucleus, and that nothing will be tangible in the world. But we know there is a bench, there is this. I am standing here and speaking. That is the biggest proof that something is there, something is possible in the universe. So that theory came to collapse, and in 1913, Niels Bohr explained it. He said that electrons can only move in shells that have a definite angular momentum. L is equals to n h by that was
This
his
is not a
conviction.
bribe, I don't do it.
So the discreteness that Planck showed, like we can put the light particles as small discrete packets. The same thing was repeated by Bohr, saying that the shells are in discrete orders. So when that happened, it was a very big revolution in physics. Same like Niels Bohr's square. Nobody was able to explain at that time how these electrons are moving, how this is happening, why can electron go in anywhere, why it has to be at some designated places only. So Bohr merely explained that, but the problem was this theory was only working for the hydrogen atom. There are 118 elements in the periodic table now. At that time, there were around 78, 79 elements, and it was working for just one element. So everybody was like, "What is this? It is not working." But it was a very big leap from what we had in the Rutherford's model. Finally, Sommerfeld came and he tried to box this up. He introduced quantum numbers. You studied chemistry, S, P, D, F, NLM, azimuthal quantum number, principal quantum number. He introduced all that to explain what Niels Bohr had done. But even that could not stop from what was about to come in the year 1924. In 1924, De Broglie he suggested that as light can be dual, particle and wave, why can't then a mass, electron particle be both electron and a wave? And this idea, this idea revolutionized physics because you will see that most of the discoveries, major discoveries that happened in physics were in the year 1900 to 1925, 1926. This was a year of golden age era for physics. Everybody, Schrodinger, Max Born, Dirac, everybody was doing their set of equations, something to come up, and that was very like everyday physics was changing. ठीक है? So De Broglie just he suggested that similarly as light can behave as a particle as seen in photoelectric effect, and it can behave as a wave as seen by experiences like diffraction and interference. Similarly, electron can also do that. He just mentioned it as a theory, but many scientists, Davidson, Kramer in Germany, they showed that electron could do interference just like a wave, and that was a breaking point because De Broglie's theory was correct. That light can behave as a wave too. Light, electron can behave as a wave too. We are all made up of electrons and protons and neutrons. If those particles are made up of waves, then ultimately we are waves. If you take it that we are waves, how can something so tangible, we can touch ourselves, we can touch these beings, how can something so tangible built on probability? That is why Einstein said God does not play dice with the universe. Because he could not believe that something small as probability of a single electron can determine how a thing will be tangible or not. So after this entered Werner Heisenberg, one of the most famous and infamous scientists of the
You made him famous.
famous and infamous scientist of the 20th century. He gave the most popular Heisenberg's uncertainty principle. He just said any particle, if you know its momentum, you cannot know its position. And if you know its position, you cannot know its momentum. There is a very classic joke about this. A police officer, Heisenberg was driving a car at a very high speed, and one of the police officers he just stopped him. What are you doing? "Yeah, I'm driving a car. You know you are going at 160 miles an hour. Shit, I don't know where I am now." That was a very classical joke about Heisenberg's uncertainty principle. So the thing is, this seems so unrealistic. Like we know where Arun is sitting. If you move, we know how much velocity will move. It is very simple about that. Why can't small particles, subatomic particles behave that way? And this is the biggest rift between classical physics and atomic physics and quantum physics. We cannot say for sure what a quantum particle is doing, what a subatomic particle is doing, and that is the reason beyond why we cannot converge both quantum physics and classical physics. And these physics are finding this today. Grand unified theory, M theory, string theory, everything is trying to converge these two theories. So the classical physics and the quantum physics. Back to our topic. All this was good until all these were actually stories. Everybody was believing everything is going good until Schrodinger formalized the equation, his famous wave equation. He simply derived the wave equation from E equals mc square. If you use E equals mc square, the same Einstein who said that God does not play with dice, he gave this equation. Now we can write this momentum as this mass as a momentum. If you write this mc dot mc by m, then we will get then we can get here p dot p square by m, something like this. So if we so what was that word? Substituted. If you substitute, if you substitute this with quantum operators E cap and P cap, you will get the Schrodinger's wave equation such as this.
Quantum mechanics, what is it?
Yes, you see the paper right there.
So I read the paper. This is general equation. If you want to add the potential term if the electron is not at rest, you will add this. For most of us, this will just be an equation, a normal equation like any other. If somebody does not know physics, it will just be an equation for him, nothing else. But those who know physics, those who know what this equation represents, they know how huge is an accomplishment this is. With this equation, we can calculate the probability of the electron inside the atom, where it can exist, where it cannot exist, and how it will behave. Schrodinger believed this was the most elegant equation he had ever written on paper, ever written in the face of the earth. And I think we must believe that we cannot know everything at once. Even if some of us will go to the research field and we will see many things, we will read about many things, we will learn many things, and we will discover many things. But at the end of the day, we will always be people with very less knowledge. We will never be able to cross a certain threshold. Even if the total, when we study physics, we study from Newton up till Higgs boson in 2013. Everything we study. Still, many of these leading scientists cannot know what will happen next, what theory is going to explain the universe next, what theory is going to make the headlines next. Everybody is trying to do this and that and this and that. But understanding what physics is all about is the curiosity. When I was a little boy, I asked why for everything. I asked my mother why the sky is blue. My mother said like it is blue because it is blue. I did not know the answer about that. Why will a cracker make a sound? Why cannot walk on ice? These are very simple questions. Very simple questions. Why do stars twinkle? That curiosity makes what physics is today. If that curiosity is dead, if you just hear two people write some equations on the paper and pass the examination, that is not physics. That is just any other subject. But the curiosity that will why this thing has to be like this? Why the equation has to be this? After this, Dirac obviously changed the equation for relativistic motion. I will not go to Dirac, it will take much time. I will not venture into that. But Paul Dirac used this equation and it came at a much more elegant equation. He combined special theory of relativity with this Schrodinger's equation. It was very good, very nice to see. On an ending note, I will just end my speech here with the most popular experiment in physics I know. It is the 1935 Schrodinger's interpretation of the Copenhagen experiment. It was everybody knows about Schrodinger's cat, the most popular experiment in physics. Simply in 1935, Schrodinger said that if you take a box and put a cat inside it and a vial of poison, that can break at any point in time, and we close the box. So we cannot tell for sure until and unless we open the box, we cannot tell for sure that the cat is alive or dead. He uses analogy to explain the quantum, the probabilistic nature of particles. For example, if you calculate the probability, for example, for 1s1, it is circle. S is circle. We all know S. S orbital is circle. So the probability is like that. So it can be anywhere. Maybe
Completely. That's fast.
maybe Schrodinger calculated the electron will be here. It may not be here. It may not be there. It may be here. We cannot know for sure. Until unless we look at it, we will not be sure where the electron is. That was the whole conclusion of the Schrodinger's cat experiment. And if you think about it, many scientists have dedicated their entire lives to quantum mechanics, to understand it, to build it, and we will study it for maybe 2 semesters, 3 semesters. Many of you will pass out without even understanding it. Relativity, quantum mechanics, they're very dense topics, very immaculate topics to understand. So at the end of the day, I would like to end my speech by thanking all of you, because you listened to me for I don't know 10-20 minutes.
20 minutes.
20 minutes at max. I hope I was not a pain in the ear for you all. Thank you.